So what we're doing today is looking at chapter 1.1. So we'll be back on the first page of that note sheet. Now, chapter 1.1, for the most part, is going to be a little bit of this, that, and everything. It is one of the only chapters that we are going to cover that each section is going to not seem to be connected at all. And in a lot of ways, they aren't. So it's going to be a little bit of this, a little bit of that, just kind of covering a lot of bases, doing a lot of different things. The entire year is not going to be like this, because once we hit chapter 2, chapter 3, we go from here. It is going to have a central theme, a central topic we're going to be hitting. Because once we hit chapters 2, 3, and 4, it's going to be quadratics, quadratic equations. Our ax squared plus bx plus c, x squared plus 2x plus 4. Those equations are what we're going to focus on. Chapter 1's a little different. It's going to be broad. And the first thing we're kind of talking about is interval and set notations. It might be a bit since y'all talked about intervals or set notations or what a set is. A set is a collection of objects. That's all a set is a collection of objects. Braces are used to list a set's members. So we offset it with braces and then put whatever the members or the objects that are contained in that set between them. That's all a set is. Now, for the most part, we're used to sets being like these two examples here. 1, 2, 3, even, positive numbers. It doesn't have to be that. We could say fruits, apples, oranges. We can say the students in this classroom is a set. Set is just a group of objects. And we use the braces as a way to define the set and be able to list all the members of said set. So if we're looking at the first example here, 1, 2, 3, brace 1, 2, 3. We've listed that set. And that set's kind of nice because there's 3 elements. Each object in the set is going to be called an element. Each element in that set can be easily listed. 1, 2, 3. That's it. Subsets are not as easy to list. Positive even numbers. Because what would be our first or our smallest positive even number? 2. It would be tempting to say 0, because 0 is even, but 0 is not positive. 0 is a little weird that way. 0 is even, but 0 is not positive or negative. It's neutral. So when we talk about positive numbers or positive integers, positive whole numbers, we're excluding 0. We're just trying to get rid of 0. We're just saying everything that is greater than 0 and positive. So our first number would be 2. What would the next one be? 4. Okay, and then 10, then 12, then 14, then 16, then 18, then... Are we going to be able to actually list all these out? How many know what an ellipses is? Or dot, dot, dot. We're saying we have established a pattern. There's no way to list all of these, but I have set a pattern. We're saying even numbers. 2, 4, 6, 8, 10, 12, dot, dot, dot. This pattern is continuing in this way. So with sets, if we can define a pattern, we give it the pattern, we get the dot, 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 it continues on. That's a set. Questions on these here? Now, not every set is going to be as easily written as this here, so we need ways to describe numbers. Why would we want that? And the big reason we do this, and a lot of this here, is not so much because we want a specific way to write it or do things. We want ways to have this described where I don't have to be standing there to describe it to you. Does that kind of make sense? And that's in everyday life. Because if parent, guardian, or whatnot wants you to do something and they're not specifically there because they left earlier, hey, we need you to do these things, we need a way to just kind of write a note, say, hey, because of how this is written, I know what I'm supposed to do. Same with numbers. I need a way for me to describe it and write it, or a way to write it, to where I don't have to be there to describe or tell you exactly what the thing means. We need a set way to actually talk about this. Just like we said with positive even numbers, there are set groups of numbers and we give them names. You've probably at least seen this at least once, but they do build on each other. And that is why we have the boxes and boxes and boxes. Now, you have one picture for this whole thing. I'm going to slowly build it on the board. Okay? Now, the smallest box that we have, inside on the top left, that far most interior box, we're going to call the natural numbers. So right there. Yep, natural numbers. Now, I can't get this rhyme out of my head because it's the only way I remember it. Natural numbers are naturally the numbers you count on your hands and your feet. Those are natural numbers. So 1, 2, 3, 4, 5, 6, 7, 8. Numbers we can count. Our counting numbers, our positive numbers, those are natural numbers. And it kind of flows off the tongue. Natural numbers are naturally the numbers you count on your hands and your feet. Makes sense? You will hear me say this now, and you will hear me say it throughout the rest of the year. And I believe it, all mathematicians are lazy. 100%. Because apparently writing natural numbers is too much. So instead, what they do is write this here and end with 2 lines. In proofs in upper level math, instead of writing out the set of natural numbers that are this, 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 and give a description, they will use that symbol. That is natural numbers. Outside of chapter 1, you won't have to use that again. But now, if you see that symbol, you know that they're talking about the natural numbers. So it almost gives us a description. When we're talking about this problem or this thing, like if for y'all that were in geometry last year, when we talk about the Pythagorean triplets, they would say that any number that is a part of the natural numbers, this symbol here is going to get this description or be defined by this here. Gives us a way to know what numbers we're talking about. We're not talking about every number, just our counting numbers. Make sense? And if you notice, we've kind of gotten some of the numbers. There are more numbers than this, yes? Well, that leads us to our next type of numbers. Whole numbers. What's the big difference between whole numbers and natural numbers? It starts with 0. That is the only difference between whole numbers and natural numbers. And like I said already, mathematicians are a little lazy, so we're going to give it a symbol, yes? What do y'all think the symbol for whole numbers is? You have a guess? What do you think? Nothing. There's nothing. There's not a one for whole numbers. Because, for the most part, if we're talking about whole numbers, they're not going to say whole numbers. We're going to say the positive integers. Or the non-negative integers. Not positive integers, non-negative integers. They skip right over whole numbers, because since we're just adding 0, we're not going to give it a symbol. We're just going to say the non-negative. Now, for us, if you want, we can define it as a W with a line. We can make up our own if we want. Because there are some assignments that will say integers. If you want to write out integers or whole numbers or this here, you can write out the whole word. Or you can use the symbol, and we'll see how that works here in a little bit. But integers, the big difference between integers and whole numbers is we're adding our negatives, our additive inverses. You kind of see what we're doing so far. We had the positives, we added 0, now we have our negatives. We're slowly building a number line. We're slowly working up with every group. And as we step up, each of the previous are still contained in that group. So a whole number is an integer because it is contained with it. A natural number, all the natural numbers are contained in the whole numbers. So if a number is a whole number, it's also a natural number. If it's a natural number, it will be a whole number, it will be an integer, but not all integers are natural. Is -2 is an integer, yes? We have it listed there. Can we say that -2 is a whole number? -2 is not a natural number, but it is an integer. We kind of see that distinction? Because we are building it up and everything in the box before is contained in the new one, but just not everything in the new box is contained in the old one. Now we do need a symbol for integers, yes? Obviously, what would it be? Oh, yes? Exactly, it's a Z with a line. Because that makes perfect sense. Yes? A lot of what we define stuff or give it symbols or give it names is not so much based off the English. It's going to be based off the root or the people's native language that came up with it or founded it or discovered it. Or another group of numbers was discovered before, integers, and got a symbol for it first. They don't double up. Because there's nothing more confusing than giving two things the exact same name and then trying to refer to each one. Yes? But integers are our positive, negative counting numbers. Questions on this so far? The next one we have is rational. Rational numbers. Now, I find a nice way to remember what a rational number is based off the first four letters of rational. First four letters of rational do spell what? Ratio. Ratio, part to part. A fraction. Anything we can write as a fraction is going to be a rational number. Natural numbers and integers are rational numbers. Like, how can we do that? Well, 2, I can say that it is 2 over 1, yes? 2 divided by 1 is still 2. It's still a fraction. We don't write it that way because it's unnecessary. But we can always put a number over 1. Anything that can be written as a fraction is a rational number. It's a ratio. It's comparing two things. We still need symbols for it, yes? And the obvious choice is Q. I never said it makes sense. It's because it really feels like we should have an R with 2 lines, yes? That's already been picked. That's already been taken. Because that would be our real numbers, our not next group, but one of them. Because our rational number is anything that can be written as a fraction. So most decimals, not all decimals are going to be written as a fraction, 0.25, 0.333. Any of our repeated numbers, just 0.333 is 1/3. 0.1 repeated is 1/9. If we can write it as a fraction, it is rational. Do we have numbers that can't be written as a fraction? Yes, you covered them in geometry last year. And Algebra 1. Pi is irrational. 3.1415926, It's a non-repeating, non-terminating decimal. Anything that is a non-repeating, non-terminating decimal is irrational. We know the top one is pi. We talk about it with diameter of a circle, circumference, area of a circle is that there. The second one is 5. You will not see that in here or anywhere else really after this. It is considered the golden ratio. If you go into liberal arts degrees and you start studying a lot of the Greek, they are very obsessed with this golden ratio, 5. Most columns, most Greek sculptures and statues are built in this proportion of 5. It is a circular art that extends out and gets bigger and bigger as it goes. The last one is E. E is used for exponential growth and exponential decay. We will cover it in the spring. Irrational numbers is given an I with 2 lines, which makes sense, but this also means that we had irrational numbers before negatives. That seems strange, doesn't it? Especially for us. We're used to negative. We're used to seeing something as a negative number. But especially when we talk about the Mesopotamians, the Babylonians, so we're talking BCE, before Common Era, before Christian era, had irrational numbers. They knew what an irrational number was. But that's also talking about agrarian society where we're counting things. Is there any reason for me as a, even now as a cow owner or kind of owning cattle, to say I have -2 sheep? No, I don't have sheep. There's no reason for me to document it, especially when documenting in paper was expensive, or trying to keep track of things is not easy. We want to keep track of what we actually have, not what we don't have. And even if you owe something, you're saying that you owe this amount. I'm not negative this amount. Negatives came much later. And yes, these are not the only irrational numbers. You covered it probably some last year. You ran into them. Square root of 2. Producing radicals where they don't reduce the nice numbers. They give you that, especially the calculator throws that massive long decimal. Non-repeating, non-terminating, non-repeating decimals. They're irrational. Any radical that does not reduce is irrational. Trying to make sense so far? Any questions so far? I already mentioned the last one, because in all of this we have real numbers. All of these are a real number. And the symbol for real numbers is an R with 2 lines. That's why rational did not get the R. All of these are considered real numbers. That also poses something, because if I'm going to say all of these are real numbers, it means what? Well, they can all be used in math, but if I have real numbers, we have to have what? Fake numbers. Now you're like, what do you mean a fake number? How can there be a fake number? And luckily, we don't call them fake numbers. We call them imaginary numbers. There is such thing as imaginary numbers, non-real numbers. And you've actually seen them. You don't have to write this down, because on the Praxis ACT, you've seen at least 1 or 2 questions so far. Solve the following equation for imaginary number I, which equals this. And they'll give you a set of expressions that look something like 2 plus 3i times 2 minus 3i plus with i's. This is half real, half imaginary. The I part, the number with I, is an imaginary number. The number in front of it, the number without I, is a real number. And I find it kind of funny because we just put real and imaginary together. So we call that complex. That's a complex number. It's half real, half imaginary. Kind of weird, kind of blowing your brain already, day two. Where would we ever see imaginary numbers? There's no way they're ever going to come up. There's no way you're going to ever come across it. The one main place that I think you'll come across it is anything that deals with electricity as we define it. Because we need equations for electricity or defining charts or defining to figure out how electricity will flow through a circuit. It comes up there. Because if something's turned off, does it have the potential for energy to flow? Well, yes, there is potential, but if it's off, there is no electricity flowing through it currently. So in a lot of those systems, for energy to flow, when it's turned off, there is no energy flowing through it. It is considered to be in the complex plane, defined by complex numbers, this imaginary part. And as soon as it's turned on, it comes back into real numbers. We can actually define it. It jumps between the two. There are some parts, we'll get to it in quadratics, where some parts of the system just are not definable. We can get a value for it, it's just not a real value. Questions on how we define a number? So, let's see how we can actually use this, because that's the big question. Why go over this if we can't use it? The set of whole numbers less than 10. So, this here, can we list them? That's the big question. Can I list whole numbers less than 10? Because what's the smallest whole number? 0. Okay? What's our next one? 1. And then? 2. And then? 3. Okay? Okay? Let's keep going. And 9. We list them all, yes? Was that easy? Was that doable? Yeah, we can easily list those. We're good there. Yes? So the whole numbers, the set of whole numbers less than 10, we knew by whole numbers we're talking about 0 and greater, less than 10, so it had to be smaller than 10. It gave us a way to describe those. So we didn't actually have to use or write whole numbers. We just knew whole numbers meant less than 10. It gave us a way to know what they were talking about. Questions on number 3 before we look at number 4? Number 4, the set of odd whole numbers less than 24. All right. What's our first odd whole number? 1. Okay. What's our next one? 3. Then keep going. Mm-hmm. 17, 19, 21. Is that it? Yep. Even though it said to 24, that doesn't matter. We said odd numbers. 24 is even, divisible by 2. If we can list them nicely, we can list them easily. We're going to list them. We're not going to have to say for all the whole numbers such that 1 is less, or 0 is less than x is less than 24, because I can easily list them. If we have a pattern, we can set a pattern. We're going to set that pattern, go dot, dot, dot. We have it listed. Make sense? What we won't do is if we cannot set a pattern or number set, then we're going to have a different way to do it. We're going to have to actually start using whole numbers. We're going to actually have to start writing expressions to be able to define the set. You all ready to do that? Okay. We'll do that after this. The next thing I want to talk about is subsets. We know what a set is. We already talked about it. It's a collection of objects. Doesn't matter what those objects are, it's a collection of them. A subset, be nice if it actually started at the top, is a set that is a part of a larger set. It is contained within that set. Is when all elements of set A are also contained in set B. We would say that A is a subset of B. If all the members of a set are contained in another set, it is considered a subset. Now for this here, we will get to numbers in a second. Let's start something that we can relate to a little bit better. Can we say that my classroom is a subset of the high school? Is every part of this room contained in the high school? Yeah, so it is a subset. Because every part of this room, every piece of it is contained in the high school. Can we say that the high school is a subset of my classroom? No, because we could go across the way to Miss Williams' room. Miss Williams' room is a part of the high school, yes? Is it a part of this room? No, because there are parts of the high school that are not contained in this room, we cannot say that the high school is a subset of my classroom. But we can say that my classroom is a subset of the high school, yes? Can we say that my classroom is a subset of Colcord, Oklahoma? Every part of this is contained in Colcord, Oklahoma, yes? Could we say Colcord, Oklahoma is a subset of Oklahoma? Yeah, every part of Colcord is contained in Oklahoma. Is Colcord, Oklahoma a subset of the U.S.? Yeah, that's all a subset is. Everything in it is contained within the other set. Okay? Let's take it one step further. Is my classroom a subset of my classroom? Is everything in my classroom contained within my classroom? So can a set be a subset of itself? Yes. So let's look at some numbers. A contains 1, 3, 20, 15, 27. It contains those numbers, yes? Set B, 1, 2, 3, 20, 11, 15, 27, 100. Is A a subset of B? Every element of A, every number in A is a subset of contained in B. Like I said, mathematicians are lazy, yes? We are not going to write A as a subset of B. That weird looking C is subset. So we can say here that A is a subset of B. Can we say that B is a subset of A? Because we do have 1, 3, 15, 27, and 20, yes? And B also has what? 111, yes? Are they in A? So B contains elements that are not in A. So B is not a subset of A because not everything in B is contained in A. Because if everything in one is contained in the other, we can say it's a subset. Or we can use letters, because we have that there. Set A is AB, set B is ABCD. So again, we can say A is a subset of B, because everything in set A is contained in set B. Just like the previous one. Can we say that B is a subset of A? Because B also contains C and D. We have an understanding of what a subset is? Not too bad. All right, let's make some. We're going to make some subsets. Now, we're writing subset in set notation, our brackets. Write all non-empty subsets. Why would they say that? So let's actually, you do not have to write this. I would not write this. So if we have bracket, 0 with a line through it, bracket, this is the empty set. That's why most math teachers, or you hear people say 0 with a line through it, don't do that, because that's not 0, that's empty set. Especially with set notation, 0 with a line through it is signifying the empty set. Why does it make a difference? 0 is a number. 0 is an element. So if I put just 0, we would say the set containing the number 0. We're not talking about a value, we're just talking about the number itself. So we can't say it's empty with 0, because 0 is a number, it's an element, it's a part of it. So we would use this here, a 0 with a line through it, to say that this set is empty. Okay, cool. We just add that and we're good, yes? I could say that I have this set containing the set that contains the empty set. So essentially, it's pretty much, if you think of buckets, I have an empty bucket inside of an empty bucket. Y'all are starting to see why that's an issue. It can go infinite. I have the set containing the set containing the set containing the empty set. And if I'm trying to list every subset, and that's infinite, there's no way for us to actually list them all out. So instead of trying to list all of those out, we say ignore anything that's empty. We're not listing those. We're not listing empty sets. We're not even going to worry about it. So if we're going to write non-empty subsets for the set 4, 5, well, I know one of my subsets would be the set containing the number 4. That would be a subset, yes? Because the set containing 4 is contained in the set 4, 5, yes? What does that also mean? We could have another subset, which is, yep, the set containing 5. There is one more. The set containing what? 5, 4, or 4, 5. For us here, for our case and purpose, 4, 5, 4, 5, and 5, 4 are the same thing. They are the exact same thing. There are some situations where 4, 5, and 5, 4 would not be considered the same thing. If you think of a vending machine, going down 4 and over 5 is not the same as going 5, 4. There are some cases where it will differ. That case, I don't think it does, but... So, for this here, we have the set containing 4, the set containing 5, the set containing 4, 5. Those are our 3 subsets. Questions on those here? All right, let's look at the other one. Set containing CD. What would our subsets be? Yeah. And whenever we do list it and we have different elements, we will put a comma between them. Now, for letters, it's not that big a deal because we can tell the difference between C and D. Numbers, on the other hand, it's a little bit different, because especially if we had in the first one 4, 5, and then 45, we need a way to distinguish between 4, 5, and 45, having them put together. Questions on any of this here so far? We have, I think, a minute before the bell. We're going to stop here. If we didn't get through all the note sheets, then that's fine. If you have a chance and want to try to see if you can list all the subsets for 2, 4, 6, you can give it a try. There should be 7 subsets for 2, 4, 6. Yes. Mm-hmm. So we will start with that tomorrow.